right, so let's take a look at probability and how this relates to entropy. If you've got some random event, let's say, what would be an example of a random event? I mean, long term, we're going to be looking at this in terms of how energy is distributed to molecules in a gas. But that can be really difficult to visualize. So what's a more everyday macroscopic scale look at something random?
A coin flip?
Yeah, maybe flipping a coin. If you flip one coin, you've only got two options. Could be heads or tails. So if you just have one single event, there's not really a distinction between microstates versus macrostates. There's just, the only options are its heads or its tails. But if we have a collection of lots of different events, let's say flipping several coins, then this becomes a meaningful distinction. Let's say you flip, for instance, 3 coins. What would be one way to describe a possible result there? Like, let's say you just toss 3 coins on the table and look at them. How would you describe what you see? Yeah, maybe heads, heads, heads. If you just have heads on the first coin, heads on the second coin, heads on the third coin, or you could describe it as amount of heads. You could say this is 3 heads. And note that these are both describing the same situation. But one of those ways is describing what each coin individually is doing. The other way is describing sort of more of a general description of the whole thing, the whole system. And in this case, heads, 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 and there are 3 heads are synonymous. These mean exactly the same thing. There's not really a difference. But if we have a more mixed description, like let's say instead of heads, 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 let's say we have heads, heads, tails. You would describe that maybe as 2 heads. But 2 heads doesn't mean exactly the same thing as heads, heads, tails, because what else would be described as 2 heads? Yeah, you could have tails, heads, heads, or you could also have heads, tails, heads. Because if you just have one tail, that tail could be in any of these 3 positions. So there's 3 different ways you could get exactly 2 heads. And we would call these 3 different ways microstates. And by microstate, we specifically mean a detailed listing of what each piece of the system is doing. So in this context, if you're flipping 3 coins, a microstate would be a listing of what's the first coin doing, what's the second coin doing, what's the third coin doing. So this is a microstate, this is a microstate, this is a microstate. So we say there's 3 microstates associated with the macrostate 2 heads. A macrostate is more of a broad general description of the entire system. And there's a lot of flexibility in macrostates. A macrostate doesn't have to be a listing of the number of heads. It could be something more like if we say all the coins are the same, that would be a macrostate. And all the coins are the same could be heads, 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 or it could be what else? Yeah, it could be heads, 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 or tails, tails, tails. So every macrostate, every broad general description of the whole system is associated with some number of microstates, some number of individual specific ways that could happen. And if you list out all the microstates, we can actually predict how many microstates we can expect before we even write them all out. If you want to know how many microstates We've got 3 coins. How many possibilities are there for each coin? Yeah, each coin has 2 possibilities. The first coin has 2 possible results, heads or tails. The second coin has 2 possible results. The third coin has 2 possible results. What do we do with those 2s? If we want to know the total number of possible results? Yeah, we can multiply those together, because the first coin could be heads or tails. For each one of those possibilities, there's 2 more possibilities for the second coin. So you multiply 2 times 2 to get 4 possibilities for 2 coins. Flip a third coin, you're branching each of those 4 possibilities off into 2 more possibilities. So that 4 times another 2, 8 possible microstates. So you can predict that, or in a more abbreviated fashion, you could just say 2 to the number of ways each event could happen to the power of number of events, if you think of each coin as an individual event. So that tells you the total number of microstates to expect. We've already counted up 4 of them manually. And notice that here we've got some overlap. We can count up the other ones. What would be the other? Oh, we also have tails, tails, tails. That's 5 so far. We should have 3 more possibilities. What are those other 3 possibilities? Yeah, we've got tails, tails, heads. And yeah, the other variants that are just one head, tails, heads, tails, and heads, tails, tails. So we now have all 8 possibilities. And calculating how many to expect in advance can be very useful, because then when you're listing it out, you can make sure that you actually have all of them. If you know in advance how many to expect, you can be sure you haven't missed any. Also, if you just toss 3 coins, what should we expect about the probability of each microstate individually? Like probability of tails, tails, heads versus probability of heads, tails, heads. What should we expect about those probabilities? Yeah, why would they all be exactly 1/8? How do we know that it's like this one's 1/8 and this one's 1/8 and this one's 1/8? How do we know that it's not like maybe 2/8 and 1/5 and 3/16 or something? What are we assuming about all these probabilities for the microstates? Yeah, we're assuming they're all equally likely. In general, if these are independent events, if all 3 coins are fair coins and they're not influencing each other at all, like this one being heads doesn't have any bearing on whether the next one's going to be heads or not. As long as these are independent events, then we should assume that all these microstates are equally likely. That tails, tails, tails is no more or less likely than heads, heads, tails, or heads, 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 or tails, heads, tails. Each one of these microstates is equally likely. This is one of the foundational assumptions that we're going to be working with for all of this probability stuff. By splitting it into microstates, we're assuming that each microstate is equally likely. Also, what do all the probabilities have to add up to? If we've got all the possibilities listed, probability of all of them added together should add up to, 1 or 100%. So if they have to add up to 1, and there's 8 of them, and it's evenly split up, 1 split up evenly into 8 pieces is 1/8. So probability of each one of these is 1/8. That's for microstates. If you want to know the probability of a macrostate, like for instance, the probability of getting 2 heads, that macrostate is associated with 3 of those 8 microstates. So probability of 2 heads would be what? Right, 3/8. Because there's 3 microstates associated with that outcome out of the 8 total. If we're assuming it's evenly distributed, 3 of the 8 microstates means a probability of 3/8 of 100%. Or we could just write it as 3/8. So this suggests that the probability of some event happening, the probability of some outcome happening, is just the number of microstates associated with that outcome divided by the total number of microstates. In fact, this is generally how we're going to calculate probability. count up the total number of microstates. That's going to be the denominator. Total number of possible microstates altogether. And then the numerator is going to be the number of microstates associated with this macrostate. So that's generally how we're going to be defining probability. An event or an outcome that is more likely just means a macrostate that is associated with more microstates. For instance, there's more microstates associated with 2 heads than there are microstates associated with 1 head, or sorry, 3 heads. So 2 heads is going to be more likely than 3 heads simply because there's more microstates associated with it. More microstates means more probable. Any questions on that so far? And you could do the same thing with other random events. Like for instance, let's say you're rolling 2 6-sided dice. If you roll 2d6, 2 6-sided dice, and let's say we are adding the results. What's one possible result you can get by rolling 2 6-sided dice and adding the results? Well, you just take 2 dice, shake them, roll them, look at the results and add them together. What's one possible result? Maybe you get a 7. Would you consider that to be a microstate or a macrostate? Yeah, that would be a macrostate because it's describing the overall result. It's a broad general description of the system. What would a microstate associated with that be? What would the microstates actually look like here? If you want a more detailed list of descriptions of the individual aspects. Yeah, maybe you get a 6 and a 1, or a 4 and a 3. And order matters here. What you get on the first die and what you get on the second die are two different pieces of information. So microstates associated with this might be 1 and 6, or 2 and 5, or 3 and 4, or 4 and 3. These do count as different microstates because this means the first die rolls a 3 and the second die rolls a 4. This means the first die rolls a 4 and the second die rolls a 3. So these do count as different microstates. And likewise, first 5, then a 2, or first a 6 and then a 1. And I think those are all the microstates that add up to 7. So these would be the associated microstates. And this is all a microstate means in this context. If you're rolling 2 dice, a microstate is just a pair of numbers. If you're rolling 3 dice, a microstate would be a list of 3 numbers in order. Just what each die is showing. If we wanted to find the probability here, the probability that the total is 7, we can make it as a fraction. Numerator is going to be the number of associated microstates. As for the denominator, how would we figure out the total number of possible microstates here? If we've got 2 events, rolling the first die and rolling the second die, how many possibilities are there for the first die? Yeah, we've got 6, right? 6 possibilities for the first die, 6 possibilities for the second die. We can just multiply those because they're independent events. We get 6 squared, or 36. So there's 36 possible outcomes. And you could list them all out. We don't actually have to list them all in order to calculate it. We just need to know how many there are That's the denominator. And how many microstates are associated with this outcome? That'll be the numerator. So you can calculate any probability this way. As long as you have some way of splitting up the event into individual microstates, and you can either count up by listing or some other way calculate how many of those microstates are associated with that outcome, divided by the total number of microstates, that'll tell you the probability of that thing happening. Any questions on that so far? And let's take a look back at the coins again. Because coins are pretty much the simplest sort of probability you can look at, just because there's only two possibilities for each event. So it's a completely binary sort of situation. And the situations we're going to be applying this to in thermodynamics are much more complicated, because we're not just taking a look at, is this coin heads or tails? We're going to be looking at things like, how much energy does this molecule have? So there's a lot more possibilities. But if we can get some general results from coins much more easily, then we can apply some of those results to more complicated situations as well. For example, if we have, let's say, 2 coins. If we just focus on how many heads there are, you could have 1 head or 2 heads, or also 0 heads. That's a possibility. For all of these, what would the denominator be? How many possibilities are there if you're just flipping 2 coins? Yeah, these are all going to be something out of 4. Because that's 2 squared. You've got 2 coins, each one has 2 possibilities, so 2 times 2 is 4 outcomes. And in this case, since there's only 4, we could list all those out. They could be both heads, or a head and a tail, or a tail and a head, or a tail and a tail. Of those, how many would count as 0 heads? Yeah, we've got 1 that is 0 heads. How many count as 1 head? These 2 both count as 1 head. So we'd have 2 outcomes, 2 microstates that are 1 head, and then just 1 that is 2 heads. So we've got a 1/4 chance of 0 heads, a 1/4 chance of 2 heads, and a 1/2 chance of exactly 1 head. So exactly 1 head is the most likely single outcome here, simply because it's associated with more microstates. If we take a look at, let's say, 3 coins, we could have no heads, or 1, or 2, or 3. In that case, what would all of the denominators be? Yeah, it should be 8 from 2 to the 3rd. We've got 3 events, 3 coins. The first coin could be heads or tails. The second coin could be heads or tails. Third coin could be heads or tails. Multiply those together, we get 2 to the 3rd, or 8. So these are all going to be something divided by 8. And without even listing them out, how many of those microstates will count as 0 heads? Yeah, should be exactly 1. 0 heads just means there's all tails. There's only one way for that to happen. And likewise, all heads, there's only 1 microstate that's all heads. As for the others, we can piece these together without actually listing it out. 1 head, if there's 3 coins, there's 3 places for that 1 head to be. Could be in the first place, or the second place, or the third place. Likewise, 2 heads means 1 tail. There's 3 places that 1 tail could be. And as a final check, make sure these all add up to 1. 1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8, so that is 1. Any questions on those so far? Or if we take a look at 4 coins. We have options of 0 heads, 1 head, 2 heads, 3 heads, or now 4 heads. What would the denominator be for all of these? Yeah, 2 to the 4th is 16, 2 times 2 times 2 times 2. So we've got something over 16 for all of these. And which ones of these are going to be easiest to fill in first, without even listing everything out? Yeah, 0 and 4, there's only one way to get no heads if they're all tails, and only one way to get all heads. Also, the next one's in, 1 head and 3 heads should be pretty easy as well. If there's only 1 head, how many places could that 1 head be? Yeah, first coin, second coin, third coin, or fourth coin. So there's only 4 places that 1 head could be. Likewise, 3 heads means 1 tail, and there's only 4 places that 1 tail could be. And note that we could reduce this to 1/4, or even write it as a decimal. But within a single type of event, it's often useful to leave it in unreduced form so you can more easily compare them. Like, it's easier to see that 4/16 is more than 1/16 than it would be if you reduced them first. And we still have 2 heads, which could be more difficult to count up without actually writing it out. But what do all these have to add up to? Yeah, they've got to add up to 1. In other words, 16/16. Add up what we've got so far. 1 plus 4 plus 4 plus 1 is 10 over 16. So we have how much left over? Yeah, so that's got to be 6/16. And notice that that outcome isn't all that likely. 6/16 is a little bit less than a 50% chance. But it's still more likely than the other ones. 1 head or 2, 3 heads, or 0 heads or 4 heads. So the most likely, if we're just looking at number of heads, the most likely result is half of them are heads. That doesn't mean it's extraordinarily likely that exactly half of them will be heads, but it's just more likely that half of them will be heads than any of the other single outcomes, because that macrostate is associated with more microstates than the other ones. Any questions on that so far? And if we extend this even further, let's say we're looking at a much larger situation. Let's say 100 coins. So you take $1 worth of pennies and toss them all on the ground. And I don't want to look at all 101 possibilities. Let's just look at the extremes. You might get no heads. You might get 1 head. Maybe we should take a look at a couple in the center. Maybe 49 heads, 50 heads, 51 heads, because we're expecting those to be most likely. And then maybe 99 heads and all heads. These are all going to have what value as the denominator, or how would we calculate the denominators here? Yeah, denominators are all going to be 2 to the 100, which is a very large number. In fact, so large that it's probably more convenient to just leave this as 2 to the 100 rather than trying to write it out in a more numerical format. Or maybe write it in scientific notation. As for the numerators, how many ways are there to get, let's say, 100 heads? How many microstates would be associated with 100 heads here? Yeah, just 1. There's only 1 way to get all heads. H, 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 100 H's listed out in a row. Only 1 such microstate. Likewise, only 1 way to get no heads, if you just got tails, 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 and so on. So those are absurdly unlikely. If you got 1 divided by 2 to the 100th power, that's so small it rounds off to 0. You're essentially never going to see that result. If you just take 100 coins, shake them up, toss them on the ground, you would never expect to get all heads or all tails. Not because it's physically impossible, but because it's so absurdly unlikely that the probability rounds off to 0. In all practical purposes, it's never going to happen. What about for one head? How many ways are there to get exactly one head in this system? Yeah, 100. There's 100 different places that one head could go. And what about 99 heads? Also 100. There's 100 places that one tail could go. And the thing is, even though that's 100 times as likely as 100 heads, all heads, this is still absurdly small. 100, I mean, 2 to the 100 is so huge that 100 divided by that still rounds off to 0. So again, not physically impossible. This could happen, but for all practical purposes, it's never going to happen because it's so remotely unlikely, such a low probability, rounds off to 0. What would be more likely? What would you expect if you toss 100 coins on the ground? Yeah, you'd expect about half heads. So if we take a look at those half here, 50, 49, 51, if we take a look at those individually, we wouldn't want to have to count out, we wouldn't want to list out 2 to the 100 values. If we actually calculate that, 2 to the 100, that's about 1.3 times 10 to the 30. So that's an absurdly large number, 1 followed by 30 zeros. So you wouldn't want to have to try actually listing all those out. We don't have enough time. And I don't just mean in this workshop, I mean in the lifetime of the universe. So way too many possibilities to actually list out. But if we can find some way of mathematically predicting how many to expect, then we can divide those and find a probability. And the formula we could use for this, you may have seen this in another math class before, the choice formula or combination formula. Usually written as NCR, and choose R. The idea here is NCR means you have N things, you're choosing R of them. So this is the number of options. And this is how many you're choosing. In this context, we could say, let's say you have, you want to get 50 heads. There's 100 places that those heads could be. So N is 100. But you're only choosing 50 of them to put heads in. So R would be 50. And the usual formula for that is N factorial divided by R factorial times N minus R factorial. Where factorial means that number multiplied by all the whole numbers less than that. Like 5 factorial would be 5 times 4 times 3 times 2 times 1. So if we actually try that out, for instance, if we want, let's say 50, 100 choose 50. That's usually how this is read, 100 choose 50. Because you got 100 things, 100 places. You're choosing 50 of them to put heads in. So N is 100 factorial divided by R is 50, so 50 factorial. 100 minus 50 would be another 50. And you could write that out and start canceling things out, but that's going to still take forever. So you just use the choose button in the calculator. 100, choose 50. So it should look something like this on a calculator, 100 NCR 50. And that gives us an absurdly large number, about 1 times 10 to the negative 29. So 100 choose 50. And then we can divide that by 2 to the 100. And I'm getting about 0.08. So still a very low probability. 0.08, there's only an 8% chance of getting 50 heads. This is still the most likely single one of these results. All the other ones are going to be less than 0.08, less than 8%. But there's so many options that the probability, the 100% we have, is spread out over lots of little bits. This is going to be the largest of those little bits. So only an 8% chance of getting exactly heads. But exactly heads is a very demanding request. If you want to get exactly half heads, that's very specific. And generally, the more specific you make a description, the less likely that description is to happen. If we make it a little more vague, like let's say we want 50 heads plus or minus 1. If we say about half heads instead of exactly half heads, we could combine these three. And for these, we'd have 100 choose 49. So that's going to be 100 factorial, r is 49, so 49 factorial. Then 100 minus 49 would be 51. Or just type 100 choose 49 into the calculator. So let's try that. 100 choose 49 divided by 2 to the 100. And I'm getting about 0.78 or 0.078. Pretty close to that in probability. And we should expect symmetry here. If you have 100 choose 51, this 49 becomes 51, this 51 becomes 49 because you've got 100 minus 51. So it's the same thing. So each one of these individually is still not all that likely. They're just more likely than all the other possibilities. But if we combine these, probability of getting 50 plus or minus 1 heads, that is 50 or 49 or 48. If we combine those, we get about 0.24. So that's almost a 1/4 chance, almost a quarter of the possible outcomes. So even though each one of these individually is not all that likely, the probability of getting about half of them heads is pretty good, a 1/4 chance. And if we expand that a little more, probability of, let's say, 50 plus or minus 5 heads, we're going to get a much higher probability. So the probabilities end up concentrated near the center. In fact, if you make a graph of number of heads versus probability of that number, you end up with very low probability of low numbers of heads, very low probability of high numbers of heads, higher probability near the middle, and it ends up following a curve like this. Have you seen that sort of curve in any statistics classes before? Yeah, this ends up being exactly the normal distribution. The normal distribution ends up showing up all the time when you're dealing with a lot of independent events. And since this is discrete rather than continuous, you can't have like 50 and a half heads. This isn't really a smooth curve. It's a whole bunch of little dots. But it's a whole bunch of little dots that follows the normal distribution very closely. And the more individual events you add, the closer those dots get to the actual normal distribution. So if we were tossing, let's say, 1,000,000 coins, then you'd have something very close to the normal distribution. If you drop 1,000,000 coins on the floor, probability of no heads or probability of 100 heads is so low that it may as well be 0. But probability of exactly half is also pretty close to 0. The probability of close to half becomes very, very high. In fact, the more coins you add in, the tighter and steeper this becomes. So if you're looking at, let's say, 1,000,000 coins, if you've got 1,000,000 coins, what would you expect to be the most likely single outcome? With 1,000,000 coins, we can assume it's never going to be no heads and it's never going to be 1,000,000 heads, right? Those are so small that it's going to be negligible. Yeah, half of a million is going to be the most likely. So 500,000. Probability of exactly 500,000 heads is also going to be close to zero because it's so specific. Getting exactly 500,000 heads is so ridiculously unlikely that's never going to happen. But getting close to 500,000 is going to be very likely. And getting few is going to be very unlikely. Getting lots is going to be very unlikely. You're going to end up with a normal distribution that's more tightly concentrated. So it's going to end up looking something more like this. Very likely to be close to the middle, about half heads. Not exactly half heads, but close to half heads. And very unlikely to be anything outside of that range. And this just gets more and more extreme the more events we add in. So 1 million coins, I mean, in terms of coins, that's a lot. But we're usually not going to be applying this to coins. We're going to be applying this to thermodynamic situations, like individual molecules. And with molecules, we're typically not dealing with 1,000 molecules or 1 million molecules or even 10 billion molecules. What's a typical number of molecules to be dealing with? Yeah, Avogadro's number. If we're dealing with about a mole of molecules. So let's say we're dealing with a mole of coins. Let's say you toss 1 mole of coins. In other words, about 600 hextillion coins. 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 coins. If you take Avogadro's number of coins, 600 hextillion coins, and scatter them on the ground, what would you expect to happen other than an earthquake? What would be the most likely single result? You toss Avogadro's number coins on the ground, yeah, about half of them being heads. And note that that's not exactly half. Exactly half is also absurdly unlikely. That's too specific. But close to 1/2, let's say half plus or minus 1%, is going to be extremely likely. In fact, our distribution graph, we've got Avogadro's number, 0, and then half of Avogadro's number. If we're dealing with that many coins, this normal distribution is going to get sandwiched in so close that it effectively looks like this. We effectively have a 100% chance of getting close to half, let's say half plus or minus 0.1%, and effectively 0 probability of getting anything else. Note that, again, that doesn't mean half exactly. It means half approximately. So half of the coins being heads plus or minus maybe 0.1% or something is going to be almost absolutely certain. Like it's always going to happen. Anything other than that is going to be effectively 0% chance, never going to happen. This is usually called the law of very large numbers. We've got a 1/2 chance of each coin being 1/2. If you're dealing with a very large number of coins, you can expect almost exactly half of them to actually be heads. And this applies to molecules as well. If you've got, let's say, energy distributed amongst a bunch of molecules, you'd expect the energy to be randomly distributed. But we're dealing with lots and lots and lots of molecules. So if you've got random distribution of lots of energy to lots of little pieces, molecules, how would you expect the energy to be distributed? Think back to what we were saying about modes. Yeah, we should expect it to be distributed equally, right? And keep in mind, this is a probabilistic thing. There's no law of physics saying that the energy has to be distributed equally. It's possible that some atoms get more energy and some atoms get less energy. But if there's so many atoms and so much energy being distributed to them, the most likely single result is energy being distributed approximately equally. Not exactly equally, that's extremely unlikely, but pretty close to equally is the most likely result. And energy being distributed unevenly is extremely unlikely, probability effectively 0. So this is where the equipartition theorem comes from. The idea that the energy being distributed randomly over huge numbers of molecules, the most likely result is even distribution. There's no reason for preference of one molecule or another, or one type of mode or another. So this is all a probability thing. And for this reason, thermodynamics is often called statistical mechanics. Mechanics means the study of motion. Statistical mechanics in the sense that each individual atom can be treated as a mechanically moving object, but there's so many of them that we have to use principles from statistics and probability to analyze on average what are they all doing. Any questions on that so far?
So is this why it's more likely for a system at a higher temperature to have heat flowing to a system at a lower temperature?
Yes, this ultimately does have to do with probability. That there's, again, no law of physics saying that the opposite can't happen. There's no law of physics saying that heat can't flow from low temperature object to high temperature object. It's just that that's so much less likely that the probability may as well be 0. So heat flows from high temperature object to low temperature object because that's the most likely result. And we quantify this in terms of so we're still talking about number of microstates. There's a lot more microstates that involve heat flowing from high temperature to low temperature than the other way around. But the number of microstates is so absurdly large, especially when we're talking about something like a mole of atoms, that we simplify it with this idea called entropy. Entropy is literally just talking about number of microstates, but modified mathematically in ways to make the calculations simpler. And it's going to look probably more complicated at first, but it becomes much simpler when we actually run the numbers. We define entropy, usually written as capital S, in terms of the number of microstates, usually written as the Greek letter omega. But the number of microstates is absurdly large. So to define entropy, we use, what's a mathematical tool you can use that cuts a very, very large number down to a more reasonable size? Yeah, the logarithm. And yeah, we use natural logarithm because it works nicely with calculus. So logarithm of number of microstates, first of all, it cuts the number of microstates down to a more reasonable size. And it also works really nicely with exponents. The number of microstates often involves some sort of exponential. As we were looking at with coins and stuff, you typically had number of events, number of outcomes for each event. To the power of number of those events. So this is often going to be an absurdly large number because number of outcomes per event is something like maybe number of ways number of different energy levels that atom could have, to the power of number of atoms, which is going to be somewhere around the size of Avogadro's number. But if you take the logarithm of that, if you're taking a logarithm, no matter what the base is, of something to a power, what can you do with that exponent inside the logarithm? Yeah, that can be brought out as a multiplier. So an exponent inside the logarithm is equivalent to a multiplier outside the logarithm. So if you've got some large number to the power of some large number, which is going to be a ridiculously huge number of omega, number of microstates, you can at least extract the exponent as a multiplier outside the logarithm, and that makes the numbers much easier to deal with. You can also use properties like if you have multiplication inside, you can split that up into addition of the logarithms. Or if you have division inside, you can split that up into subtraction of the logarithms. And this plays really nicely with the idea of delta entropy. If you're looking for a difference in entropy, you'd be subtracting final minus initial. But logarithm of final minus logarithm of initial becomes logarithm of final divided by initial. So it provides a really convenient way of combining deltas, something minus something. Also, this still tends to give you absurdly large numbers, and it ends up being unitless. We want this for other reasons to have units of joules per Kelvin. So we actually define this in terms of logarithm of number of microstates multiplied by Boltzmann's constant. So the Boltzmann's constant both cuts it down to an even smaller size, more reasonable to work with, and also gives it units of joules per Kelvin, which we want for other reasons. So this is actually how we define entropy. This is what entropy is. Entropy is often described more conceptually in terms of the amount of disorder in a system, but that's not really a real physical thing. It's more of a conceptual description of what we think the system looks like. But what entropy actually is, what entropy means is number of microstates, modified by logarithm and Boltzmann's constant. But when we say the entropy of a system has increased, we just mean the system has changed in a way that means more microstates. If we say entropy has decreased, then the system has changed in a way resulting in fewer microstates. And this ties into probability. Higher entropy means more microstates, which means more likely to happen. So entropy is likely to increase simply because that involves more microstates and therefore a higher probability. Any questions on that definition? So keep that in mind as we go forward with this. Anytime you're looking at entropy, just remember entropy means number of microstates. Mathematically modified with the logarithm, but entropy really is just a description of how many ways something can happen. We'll look into more ways to calculate that and some more examples next time. In the meanwhile, feel free to email me if you have any other questions or if you'd like to request any examples for next time, and I will see you later.
Thank you.
You're welcome.